Hello everyone, welcome to the 5G Massive MIMO training session number 7. In today's video actually we are going to cover and focus on the part related to the beam failure detection and beam failure recovery as mentioned in the bottom right here. If you remember or you can recall, in the previous 6 sessions we had covered a very important information about in general what is the meaning of massive MIMO, beam forming, and what kind of massive MIMO gains we can observe differences between single user MIMO, multi-user MIMO, and many important information including the beam management and beam forming deep dive and so on. So in today's video we're going to mainly focus in the beam failure detection and beam failure recovery, and we'll try to support our session with some of UE logs and also with the parameters being involved in both procedures. So let's move forward to see what we have today. This slide actually like cover a very high level introduction about the meaning of beam failure and recovery. Just to quickly explain, in general, the beam failure recovery and detection is like consisting of two steps or two parts. The first part that the UE himself should receive some parameters from the GMB to guide him how to detect for example, the beam failure detections or even the radio link failure detection. And I will explain shortly the main differences between both of them. If you remember in the traditional or legacy MIMO or legacy 4G, for example, we can detect the radio link failure through the some particular timers, which is T310 or N310, N311. Also, will be explaining that part. And this is mainly was being detected through the RRC layer. So what is the main differences now we have in 5G massive MIMO in general? In 5G massive MIMO, we have actually two steps of detection in general, the radio link failure. The first one called beam failure detection and failure, and the second one, it can be the radio link failure. So what is the main differences? First of all, don't get confused or consider the beam failure, which is the second one here, beam failure, and the radio link failure, which is at the RRC layer, beam failure at the MAC layer, and radio link failure at the RRC layer. Don't consider both of them as the same phenomenon, okay? Because in general, in a multi-beam scenario, specifically, okay, in the high frequency, which in short words can be the midwave, the radio link failure detection, which is happening at the RRC layer, occurs when there are a radio communication issue within a cell that cannot be resolved through or resolved by or through the recovery procedures or the beam failure recovery procedures. So what it means by this? This means, for example, when the user UE or the device is unable to find any suitable beam, and the random access procedures which is being used to recover the beam failures failed as well to recover the connection between the GMB and the UE for a specific beam. So this will be considered as all the beam failures has all the beam are not suitable. So it will move forward to the next step, which is a radio link failure to try to recover the complete connection between the UE and GMB. So on the other hand, the beam failure happens when the UE loses the link from one beam, only one beam, assuming that you have 8 beams, for example. As for example, the bottom right example here, assume that we have like multiple CSI-RS beams as 4 CSI-RS beams. So let's assume the user was camping in CSI-RS beam 3. So he lost this one. So he's trying to recover this one. This is actually trying to camp or find the next best beam within the cell, or within this beam. For example, we have here 4 beams. So he's try to monitor all of them to find the best one, to try to initiate a new random access procedures to try to recover the beam failure, which was at the CSI-RS 3. So, so once the UE can establish a connection with another beam, for example, here let's say CSI-RS beam 4, successfully, then the random access procedure works as expected. So this can recovering the beam. So no need to move later on to the radio link failure detection, and this can be happening even at the MAC layer only. And this is also involving much less signaling, and also there is less interruption from the UE perspective because we didn't reach into the layer 3. This will be only mainly happening between the physical layer and MAC layer, which is L1 and L2. So the beam failure, you can consider it as a first step to try to recover the connection before moving to the radio link failure detection. But in the real world scenario, for most of the networks which we currently have, for example, most of the network now are using the mid band or the low band, which is can be FDD or TDD, for example, 3.7 or 2.5 or 2.6. This is mainly involving the radio link failure, and for different reasons. First of all, that the kind of losing the beams, this is not as easy compared to the milliwave or high frequency. And also on top of all of this, in many of the current actual deployment, we don't have this kind of different beams. For example, for the CSI-RS, it can be only wide beam or very less beams. So mainly now the main actual or theoretical, practical involved procedures is a radio link failure. And as we going to recap the knowledge about it, it's exactly same as whatever we used to have before in 4G. And I have a separate video explaining this one. I will be also adding this one in the video description. But again, I will be recalling all the information about the RRC, what kind of parameters being involved, and I will be doing the same as well today for the MAC layer, how the procedure is being happened, how the user detect the failures, how he initiate the recovery, and what kind of parameters are being involved in all these procedures. So this figure summarizes the following. First of all, the physical layer, the user will be monitoring the beams and also the overall beams and also the complete connection, okay? So the user will be initiating something called out of sync indication in case of if the, for example, radio condition, let's say the coverage or the block error rate is falling below a certain threshold. It's called Q out. And this is usually hypothetical like BDCCH error rate. So for example, let's assume that 10%. So if the block error rate is going above 10%, so the user will be initiating, for example, a beam failures instance to the MAC layer, telling him that I have a failure. So for example, there is a parameter which is in the MAC layer. This is, for example, called beam failure instance maximum count. Let's assume this parameter is 3. This means the user, if initiated 3 within a particular time, this means now, or this is indicating or confirming there is a beam failure detection. So once the beam failure detection is being achieved or reached out, so now the user afterwards will try to find the second best beam to try to initiate a random access procedures for the recovery. In case of all the procedures failed, so now he move forward into the RRC radio link failure and try to recover the connection, for example, through initiating RRC reestablishment if again the connection completely lost or announced or triggered the radio link failure. So again, here there is two steps. In case of, for example, high frequencies, but in case of the current networks, most of the things happening through the RRC layer. So here is a certain parameters. First of all, will be delivered to the user. So the user will be generating this kind of out of sync, in sync in case if he was successfully able to decode the beams or the connection of RRC, then he will be generating either beam failures instance or out of sync and in sync indication to the RRC layer. Okay, and as you can see here, they just mentioned that the configuration information, beam failure and beam film recovery parameters, all of this will be delivered to the UE either for the MAC layer or for the RRC parameters, and also for the RACH procedures dedicated for the beam failure recovery will be also initiated to this particular UE. If you read all this kind of information on the left here, we're just repeating some of them. For example, here it's meaning that 3GPP specifies that UE applies radio link monitoring to the primary cell, okay, of the master cell group. And in case if the user is configured with a secondary cell group, which is, for example, SCG, then the UE also applies radio link monitoring for the primary secondary cell. So it can be for both of them, depending whether we have the secondary cell already being available or not. Okay, and also one important comment that radio link monitoring applied only for the active bandwidth part. The UE is not required to monitor bandwidth parts which are inactive. Okay, and again, this is as highlighted can be done on MAC layer and also RRC layer, depend on the situation and depend on the network configuration, depend on different things from the implementation, from the capability of the vendors and these kind of things, depend on high frequency or low frequency or mid-band frequency and so on. And in case if no reference signals are being configured, for example, for the detection or these kind of parameters not being configured, So the user can use something called TCI states for the core set used to receive the PDCCH to maintain the KCL relation. This is actually like a kind of a completely different topic. I will be trying to cover the TCI in general or the KCL relation, quasi collocated location. This I will be try to cover in a separate video because this contains a very important information and interesting information. So now let's move forward to cover both procedures, which is radio link failures and the beam failures, how it's being the failure detected and how the recovery can be done. And I will be starting first with RRC because probably will be very familiar about it, so we can ease the understanding from the next one, which is about the MAC layer. So let's move forward to see what we have about RRC and MAC layer in more details. So the first part we are going to cover in more details, it's about the 5G radio link failure at the RRC layer. So actually we have already highlighted this one multiple times, and I believe you might be aware about it already. So initially, this is whenever there is a connection lost between the UE and JMB. So the user need to, for example, declare that there is a radio link failure and afterwards to try to recover the connection through, for example, initiating a radio link failure and trying to do RRC reestablishment afterwards. So first of all, there should be something delivered to the user to guide him how or when it can consider the link as failed or not. For example, to consider to trigger radio link failure, to announce that the radio link has been failed, and to try to trigger afterwards the RRC establishment in case of the radio link failure has been declared. So these parameters in the bottom left here, which is contains RLF timers and constants, this will be usually delivered to the user through different messages, depend on standalone, non-standalone. I will be explaining both of them, how we can check from the drive test or layer 3 in general from the next slide. So we have, for example, T310, N310, and N311. T310, this is the timer, which is, you can see starting here. I will be explaining what is the differences between them. But for example, this is a timer. And you have in 310, this is related to the out of sync indication when the user detects that there is, for example, the particular threshold, which is indicating that you have a coverage loss. So in this case, the user will sending this kind of queue out as of extension shortly. And you have in 311, this is in case if the user is able to recover the connection. So let's explain this one as mentioned in the bottom right here. So as you can see from this particular table, actually, which is having a configuration 0 and 1, blare out and blare in, block error rate out and block error rate in. As you mentioned, and as mentioned, the bottom left comment here, the base stations or the GMB configures the U with a pair of block error rates targets, which is this one can be 0 and 1. For example, block error rate out, which is this one, 10%, corresponds to a quality of level. This is quality of level. For example, if the user is falling below this block error rate 10%, let's assume you have currently 11%. So in this case, this means a radio connection is considered to be unreliable or there is a problem in the connection. So in this case, the user needs to send this kind of called queue out that I have a problem in the connection. This is indicating there is a failures. So this one, the first, for example, count here, this is representing, for example, in 310. So in case if this in 310 is configured at 3, this means the user will not declare the radio link failures unless he reach into 3. A 3 like 3 consisting the reporting of this queue out whenever the decoding of the PDCCH is falling below, for example, 10%. So this is as a 10% here. So for example, 11%. So the first decode of the user was worse than this particular threshold. He reported the first one, second one, third one. But before the user directly to report the radio link failure, there is a process giving the user a chance to try to recover the connection, which is involving the second parameters called N311 and the third one, which is called T310. For example, this is a timer. We'll start with the whenever the N310 is being reached. For example, here N310, 1, 2, 3, 3 times reporting out of sync. So in this case, T310 will be starting, allowing the user or giving the user a chance to try to recover the connection. So the user again will be decoding the PDCCH trying to see what is kind of block error rate he have now. So for example, if he is getting a block error rate better than 2% or around 2%, which is the second pair of block error rate, this is means QN. So this is like corresponds to the quality level at which the radio link is categorized as being reliable. Okay, so in the case if the user is being able to decode a connection, so for example here, if we assume this N311 is considered as 2, so if the user only detected 1 within this timer and the timer expired before the user send the second QN, so in this case the user would declare a radio link failure and radio link failure will be declared, and afterwards the RRC establishment which is involved with the 311 timers will be started afterwards. So in case if in 311, which is currently as in this example configured as 2, is being reported twice before the 3310 expiry, so in this case, the connection will be recovered and the user will not declare the radio link failure detection, or the radio link failure in general will not be declared. This is the normal radio link failure procedures as we mentioned before. So you should now think about it. In case if you are increasing the N310, which is 3, for example, increase it to 5, you are expecting to get maybe a better drop error rate and a less RLF detection. But in the same side, this is, can also increase, for example, the interference in your network or the resource consumption, because you are keeping the users in a very bad radio condition for longer time. So this is increasing your UE power. And by the way, the UE will not in general, like there is, this is dependent on the UE implementation. He will not stop transmitting in the uplink unless he declared the radio link failure, and also the GMB will not be in sync with the user, whether the user is out of sync, out of sync or not, unless he declared the radio link failure. And also in case he increased the 310, this will be also resulting in the same. You're giving the user more chance to try to recover the connection and to reach into in 311. So the higher the values, you might get a better drop rate, but on the same side, it can impact the network interference. It can impact as well the resource consumption in the network. Now let's move to the next slide to see how we can check these parameters from the UE logs or from the layer 3 messages. So again, as you can see, this RLF timer and constants, you can check it actually from, first of all, 5G standalone RRC configuration message, or a message called cell group configuration, for example. You'll find that after here, at the bottom left here, this is the structure UE cell group configuration. If you move down here, you find multiple parameters about the RLC, MAC, timers, and these kind of things. Then under the physical layer, because this is again under the physical layer, you will find under the SP cell configuration, you find this RLF timer and constants, and you'll find all the 3 parameters which is being highlighted here, T310 and 310 and 311. This is from a standalone perspective. Non-standalone, during the SGNB addition, you'll find it again within the RRC configuration message. Again, you'll find these 3 parameters under RLF, timers, and constant. There is kind of additional or the same parameters can be detected in the very beginning, or can be checked in the very beginning during the attach or during the moving from idle to connected mode from SEB1 messages in the standalone. You'll find the same parameters, which is one additional parameter related to 311, which is actually, this one will be starting directly after the user declared RLF. The user will try to now trigger T311 would be starting, because the user will try to initiate RRC connection establishment to recover the connection. So this timer is allowing him to, giving him a chance, like waiting from the user perspective until he sent the RRC connection establishment request. In case if this timer failed, like for example, expired before the user sent the RRC connection establishment request, so this will be considered as failure, and the user cannot anymore resume the RRC connection establishment request. So this is all about the radio link failure. Now let's move for more interesting details about the beam failure detection in case of the MAC layer, not the RRC layer. So let's move forward and see what we have. Now let's continue the second part about the 5G beam failure detection at the MAC layer. The previous one we was just explaining about the radio link failures in general and at the RRC layer. And as I highlighted, usually the previous one is now the currently most common use in most of the networks because we don't have the concept, or we have it, but it's not being applied, especially in the mid band and the low band, which is FDD, NR, or TDD, for example, 2.6 and 3.5. So this is generally, you can find it more at the milliwave and the high frequency bands. If you read in the comment in the top left here, this is highlighting that the beam failure occurs when existing beams become unreliable before a UE switches. And again, can be due to obstacles or movement, for example, problems in the current beam, specifically in the frequency range 2, as I highlighted, which is the high frequencies, which can cause a rapid beam loss. Okay. And in general, this concept of the MAC layer, the beam failure detection and recovery at the MAC layer, this is very important because this is actually minimizing the delay, as mentioned here, because the beam failure detection and selection and recovery occurs mainly at the MAC layer without involving the higher layer, which is the layer 3. That's why, which is including, for example, the RRC. That's why it's kind of minimizing the delay. Now, as a concept or as a perspective of how the user can detect the beam failure detection and initiating the beam recovery, for the beam failure detection, it's exactly the same concept as whatever we had discussed in the previous slide related to the radial link failure detection, which is, for example, was covering or including different parameters, which is in 310, in 311, and 310. But what is the main differences? You will find in the table in the middle here. You have something called the radio link monitoring configuration. This is usually will be delivered to the user within RRC configuration message to deliver him these two particular parameters, okay, to explain for him, for example, in case if he detected again that the current beam is following below a particular threshold, for example, the coverage or the blockage rate is falling below a configured threshold, same as whatever we have highlighted in the previous slide. For example, again, uh, out and in, which is player blocker rate 10%, and for example, 2% at the previous one. And the beam failure is detected when PDCCH reception degrade below, for example, the 10% target. So in this case, if the user cannot decode the PDCCH, you will be reporting something called, as highlighted in the figure here, something called beam failure instance. Okay, but for how many times? What control this until the user declared there is a beam failure detected here, or there is a beam failure detection using this particular parameter, which is called beam failure instance maximum count. For example, this one I'm assuming here is applied at 3. So from the counter perspective, the MAC layer maintain this counter of this particular parameter at 0. Once, for example, the user decoded the PDCCH reception is below this particular blocker rate, which is 10%, in this case, he will be reporting the beam instance failures for the first one. So this counter will be increasing to 1. Then there is a timer will be starting, which is the second timer, waiting for the next reporting as a beam failure instance. So now within the timer, the user reported again a second one, beam failure instance, second time, so the counter will be increasing to 2. Then again, this timer will be actually, once it's being reported, it will be restarted. The timer will be starting again. So waiting again for the third one. So after the third one being received and the counter and parameter uh, value was being converted at 3, so this means there is counter will be now after the third one being initiated. This is a third one, so the MAC layer will consider this one of the user as a beam failure detection, and afterwards it will try to start the process of the beam failure recovery through searching for the best second beam to try to do the right procedures as will be explained in the next slide. So again, this parameter is 3, so the user need to decode the PDCCH 3 times. If each time falling below the 10%, so it will be reporting this maximum count until it reaches to the maximum limit of the parameter value to declare there is a beam failure detection or detected. So what is the use of the second case? I mentioned to you that this timer, which is called beam failure detection timer, as mentioned at bottom left here, assume the first one was being detected, so the counter was increased to 1, meaning that you have a beam failure detection as 1. So the beam failure detection timer will be started here. So assume that two things, even that the signal quality become much better, or the user in general stop to report the beam failure detection, which is the beam failure instance in some cases. So the MAC layer of the user will not wait for forever until it's declared the beam failure detection, right? So in case of this counter being expired without you receiving any beam failure instance, so the MAC will reset the BFI counter, as you can see here. This is called BFI counter, which is beam failure instance counter, which is the called beam failure instance counter, will be like resetting and assuming there is no any more ongoing beam failures as highlighted here. And in this case, the connection can be like kind of assuming as being recovered of this particular of the served beam. Okay. One important note to highlight is about the second parameter, which is called beam failure detection timer. Practically, I didn't yet work on that, but just theoretically, this should be the case here. Whenever you consider the settings of this timer, so you need to consider the bottom left rules, which is being highlighted here. For example, here, the beam failure detection timer, the duration should be considered that maximum of 2 milliseconds or beam failure detection RS. For example, if the DRX is disabled, this should be settings. And also with different settings. Whenever the DRX is enabled with less than 320 milliseconds, so this is the rule, which is can identify what kind of settings, for example, to be used here. So you need to consider this whenever you are facing this one in the practical scenario. In case if I work in the future in any of the cases involving these kind of parameters from the practical perspective, I will be sharing this back. I will updating the materials and sharing back with you in case if I working in similar thing from the practical perspective. Now, this was about how when the user will be initiating that the current served beam as considered as a failure or a beam failure, or the current beam has been failed, or the beam failure in general being detected for the current serving beam. So afterward, still there is no radio link failure being initiated. Still the user didn't declare like he will try first to recover the current beam before trying to take to the next step, for example through considering drop or try to initiate, for example, the radio link failure from the RRC side. Okay, so in this case what you need to do, you need now to start something called a beam failure recovery, and this is what we are going to discuss in the next slide with some of the parameters. But I will take you first through some of the description of the main parameters, which is being highlighted here, just for your record. You can just take it as a snapshot or whatever. For example, here I'm just giving you the explanation of the BFI counters, which is highlighted here for this one, and the beam failure instant maximum count, which was this parameter, and the timer, and also some of the thresholds being used to identify the second best beam during the best beam recovery. For example, if the beam is better than threshold or less than threshold, this one. So, and this is just the radio link monitoring RSID, which is actually this is used to identify one radio link measure RS. You can take a snapshot from this one, but now let's move to the procedures of the beam failure recovery. Now we explain the detection, now we'll explain the recovery procedures. Actually, for the beam failure recovery, it's also happening at the MAC layer, and it's very simple because you should be very aware about it, because actually this is just following the normal RATCH procedures with some additional parameters and also some additional related parts related to the RATCH procedures out of the normal contention-free random access procedures or the contention-based random access procedures. I will be explaining this one as well in the next slide on top of this one, but this is you can consider as a normal one. For example, there is two types of the RATCH, right? Random access procedures, right? Contention-free random access and contention-based. Contention-free means that there is a probability to have a conflict or like for example two users initiating the same random access procedures, right? Random access preamble. So the user might receive from two users the same random access preamble, so there might be a competition, or the UE might compete with other UEs to try to access the network resources, for example the beam. So whenever you have a beam recovery, the user needs, after declaring there is a beam failure detection, you need now to initiate a random access procedures in case if he found the best beam second beam, and the best second beam is based on a particular RSRP threshold being identified. So he measured, he found that there is a best beam was a particular level, So he will be initiating this kind of random access procedure for this particular beam. So there is a two types: contention-free random access procedures and contention-based. So actually, the contention-free random access procedures, as I highlighted before, for example, once the beam failure being detected, the failed, the user will be selecting the second best beam. As you can find here, this is the main high-level steps: beam failure detection, selection of the best beam, then initiating the beam failure recovery (BFR) request through the random access procedures. So he will be sending random access preamble to message one to the GMB. Then the GMB will be responding with RAR, which is random access response, message 2 within this RR response window. And this is configured actually parameter. If you increase it as well, you are giving more chance to the user to receive the response, or even to the GMB to, if there is kind of a delay in the downlink, to send it as well. So this is, can improve your random access procedure in general. Then afterwards, the user will be initiating the scheduled transmission. Then there is assignment for the uplink grant related to the resources of the PUCH through the contention resolution. Once this forward procedure is being detected, this means the beam failure has been recovered in this case. The beam failure recovery procedures has been completed. And this procedures for the contention free is just used as a backup whenever the contention base is not visible, as mentioned here, or has not been succeeded, for example, in recovering the connection after the beam failure. So in general, the more one which is going to be followed by the user related to the contention based random access procedures, because user usually the GMB would be assigning the specific preamble which is need to be used by the user to be initiating this one, to initiate the random access preamble, to avoid the conflict with the other user or the competition with the other users. So this is usually the normal procedures, but in case it didn't work, failure or not visible in general, so the user will be initiating the contention free random access procedures. So again, very simple: beam failure being detected, second beam being selected, the GMB will be delivering the specific random access preamble for this particular beam, which is being selected by the user or expected through the reporting for the user, that expecting that this beam is the best one. So the GMB will be allocating the random access preamble for the user. Then the user will be initiating the random access preamble with this particular one. Then directly the random access response will be coming back, and the probability to get this one success was much higher than this one, because you don't have this kind of random sending random access preamble. So once the RAR being received, this will be considered as beam failure recovery here. So 3 steps to through the detection, 4 steps. Actually, it's happening after the first of all beam failure detection. The beam failure, as we highlighted in the previous slide, detected, the beam detected. Then the second step, the user will be measuring he will be already monitoring all the beams, and if these beams was better than this particular threshold, which is called RSRP threshold SSP or RSRP threshold BFR, beam failure recovery. So in this case, the user will be initiating the beam failure request, even contention free or contention based, and these 2 steps considering both the complete random access procedures. So I highlighted that there is additional like signaling flow for the random access procedures, which is also tried to be followed by the GMB and the user to try to minimize the delay during the beam recovery whenever the user is trying to initiate the random access procedures. And I'll be explaining this one in the next slide. So as I highlighted here in the bottom right here, this is in case there is already a configuration being sent from GNB to the user and so on, and there is a beam failure being lost, and this is in case of the contention free, which is similar to this one, and assuming that there is no contention based here. So some procedures being followed by GNB and user to try to speed up the connection of the delay of the recovering the beam. Okay, so if you read in the bottom top left here, in the case of beam failure recovery, the base station responds to PRATCH preamble by sending a PDCCH transmission which addresses a UE by HC RANTI instead of RA RANTI, random access RNTI. Okay, so what it means by this? So you'll find this here: beam failure is being recovered as similar as these steps. Then the user select the best beam, initiating the random access procedure, which is message 1. The normal procedures should be that receiving random access response, scheduling transmission, contextual resolution, and so on. But this will not be the case. Actually, the random access procedure is then categorized as successful. Like why? Because in this case, the GMB know all the information about the CRNT about this particular user, so it will be directly replying with PDCCH DCI format 10, allocating the resources directly for the user using this CRNTI instead of RNTI. And as mentioned here, the random access procedure is then categorized as successful without the requirement to decode random access response with a MAC sub PDU, which was this particular procedures. This is just used to minimize the delay. So again, this is like kind of a detailed steps followed by the user to try to make in general the beam failure recovery. For example, first part, you need to identify the target beam, which target beams he would like to monitor, how many beams, for example, 3, 4, 5, depend on how many beams being configured in the network. Then he will measure the coverage for all these beams. For example, the coverage better than this particular threshold, RSRP threshold SSB, user will measure all of them. Once the beam is better than the threshold, then if the RSRP meet the threshold, then the beam is selected. Then afterward, the user will be generating the RACH preamble, and there is a different configuration, usually delivered under something called BFR. I'll be explaining this one next slide, how to check it from the layer 3 as well. So the user will be generating the preamble using specific root sequence index, root sequence, and the configuration. Then also using some particular parameters within the range, the user will be considering that to select the time and frequency resource related to this PRATCH. Then he will be transmitting the PRATCH, and the power of PRATCH will be calculated using these three parameters, which is preamble receive target power, preamble transmit maximum, how many times can be transmitted in case of fail, and what is the power ramping step in case of also a particular failure to try to recover the failure of the random access transmission. Then there is a parameter to wait for the response for RAR, which is called RA response window, waiting for the GMB to respond with a response PDCCH. Then there is a random access procedure, some other parameters. If no response, the UE will try to parameterize random access through some particular parameters. This is kind of a very detailed one. Then again, this is including all the steps. Now, the last part in this, I will be showing the parameters of the RATCH, how to check from the layer 3, and usually which one you can directly know these RATCH settings are related to the normal RATCH or related to the random access procedures involving the beam recovery. So let's move to the next slide. So again, you'll find you see the parameter on the left here, the parameters on the left here. You will find after something called beam recovery configuration, you sort of find after this particular category, you'll find something called RATCH configuration BFR. This is must be BFR. BFR means this is for beam failure recovery. Okay. So for example, the parameters I'm showing on the right from the layer 3 here, this is not for the actual beam failure recovery, but is exactly the same. For example, this is RATCH configuration generic. This is for the overall random access procedure in general, not particularly for the beam failure recovery. This means in case if I have this kind of MAC layer for the beam failure recovery configured in the network, you can control a complete different parameters for the RATCH for the beam failure procedures only. In the MAC layer for the beam failure procedures, different to whatever you have for the RATCH procedures in general for the other normal procedures, for example, including during the RRC, during the handover, this kind of things. It's including the same parameters, but it can be different things. So it will be again within the RRC configuration message dedicated the active or the active bandwidth part. So you'll find this one. You'll find, for example, all these parameters, which is including the PRATCH configuration index, the frequency division multiplexing, what time of message, what frequency start, the correlation zone, preamble receive target power to identify the increase of the initial power transmission using the PRATCH, how many times you can retransmit the preamble, the again RA response window, and see all these kind of things as you can see here. Also, there is another thing related to the as highlighted in the previous video, for example, the mapping between the SSB and the PRATCH in general. This is also a different thing. We already discussed a high level, but I will go through this one whenever I discuss the random access procedures in the different videos. Then you have this kind of threshold called RSRP threshold SSB. This is, for example, in case of the beam within the SSB being failed, so you'll be locating the best beam, the second best beam based on the threshold as highlighted in the previous slide. And the next slide, actually, again, this is going through the explanation for each of these parameters highlighted in the previous one, in case you would like to take a snapshot for your reference about the description for each and every single parameter, which will be explained in much more detail whenever we reach into the video of the random access procedures. We'll try to cover everything in more details about the random access procedures in general. And actually, this was the last part about today's video. I hope if you like the content, again, to press like and to spread the knowledge and to share it with your colleagues and friends. And thank you very much and see you in next video.